Hello, this is Jeffrey Fox. We now come to Unit 3 of the physics use case, where we get into a little more detail about how to analyze the actual events, introducing the concept of random variables and the properties of random variables, which underlie the statistics used in this problem. As always, we're using clouds, running data analytics collaboratively, processing big data at 15 petabytes a year to solve problems in physics informatics. And we haven't been able to find that term on the web yet. So let's first discuss random variables in general and in particular as applied to physics. This list here represents the topics and random variables that are to some extent covered in this use case. This is not a course on statistics, but it is an example of using statistics to solve a particular use case, that of analysis of physics data. So we will, at the end of this, if you want, you can say you've learned the following things. You've learned what a random variable is. You will have been introduced to independently identically distributed random variables, which are what you get in physics, because when those particles collide, two protons collide, each event is independent, coming from sort of the quantum mechanical underpinnings of those collisions. Then we have something pretty important, the law of large numbers, that the error is proportional to the square root of the mean. And we have already something we've already introduced, counting experiments, which count numbers, number of times things happen. We have important distributions. First, the Gaussian or normal distribution, which you get when you look at the distribution of the average of large numbers of independent random variables. You have important consequences of either having too few observations or too few experiments. That's the statistical error side of things. We also have the systematic error or bias, which is in practice more important because we know what to do with statistics, we just run longer. If we've got the wrong answer, it's not so obvious what to do. That's a systematic error. But we have to estimate both. And to do systematic errors, we won't really discuss that in these lectures because that you have to know a lot of physics to disentangle the systematics of a particular experimental apparatus. We will discuss how to generate random numbers and how you use seeds to start off a sequence of random numbers. We will discuss binomial distributions. We will discuss signals and backgrounds. I've already seen that in the last unit where we had a Higgs signal on a sloping background. We will define a little better something we've introduced, an example, namely the accept project method for generating random numbers with an arbitrary distribution and an arbitrary number of dimensions. We will discuss the Monte Carlo method, which is essential for understanding apparati in this particular example. We will have another important distribution related to the binomial distribution called the Poisson distribution. We will have the central limit theorem, which underlies the theory of a lot of this material. And then we have a little diversion at the end of the Unit 4 on frequency versus Bayesian interpretation of probabilities. And also Bayes' rule, which is a very important rule for combining information. So all of these things are, at some extent, at least mentioned, if not deeply covered in these lectures. So let's think about a random variable in the physics of the Large Hadron Collider. As we've said already, the area of probability and statistics is the analytics that underlies the analysis of physics data. And I first started doing this, I don't know, too long ago, 1970 or something. That's quite depressing. And at the time we did it in those days, physics was probably one of the largest examples of the application of probability and statistics, because the physics was already big science, doing big experiments, and so they tended to gather more complicated data than anybody else. Now it's not so obvious that's true. We get lots of data of all sorts of types automatically on the internet, and Maybe Twitter is more or Google search is actually a better example today. But in those old days, lots of the important text on statistics came from physicists who were using the basic theory done by typically mathematicians to analyze data. So as we already remarked that the LHC, a proton collides with another proton or actually a heavy nucleus when they want to do probe what happens in the plasma when you really hit a nucleus with very high velocity, high momentum proton, and say there is the sort of fundamental quantum mechanics of those interactions says that whatever happens is random, and the result of each collision is independent of the previous collision, and they run over an incredible set of possibilities because those possibilities are labeled by hundreds of real numbers, which are the momenta and etc. of the various outgoing particles. And then if we were able to calculate the theory of proton-proton collisions at high energy or affected any energy, we would be able to calculate these probabilities. That's quantum mechanics predicts the amplitudes and the square of the amplitudes of the probability, and you should be able to predict it. As I mentioned, actually you don't calculate the theory precisely. You make models which approximate the theory. You use those to interpret the results. And I think I mentioned historically, I used to work in this area of building models. It was called particle physics phenomenology, and I worked with distinguished people like Richard Feynman, who taught me how to do some of those modeling models. So we have these collisions, which are all random. And then we have results, which the results are actually caught events. These are very complicated events because they record everything that happened in the collision. And they represent a random variable, which is a sort of vector, because there's lots of results. And that vector, in some sense, has a different length on every collision, because you produce a different number and type of final state on every collision. And of course, such events, which are isolated independent activities, are very important, where you earthquakes, stock transaction, and bank transaction are also, of course, other types of important events. Then we have our famous data, information, knowledge, wisdom pipeline, which transfers this raw data into the wisdom that the Higgs boson exists, starting with the data, which is the stuff that happens when those protons collide at the LHC. And at each stage of that analysis, you're actually taking events and converting them into new types of events with transformations, and those are new types of random variables related to the old random variables. At each stage, you retain the independence between the different collisions, but there's, of course, huge correlations with the results within a collision.